Good afternoon, everyone. My name is Ismael. I'm one of the co-founders of Lagrange Labs. So today we're going to discuss ZK coprocessing. ZK coprocessing is a term that I hope some people here have heard, but it's one that I think is often ill-defined. So what is ZK coprocessing? Put simply, it's a new way to answer a question in crypto we've been asking for 10 years. How do we scale blockchains? We've looked over the last 10 years at a variety of different approaches to scaling on-chain computation, ranging from different consensus designs that have reduced security assumptions by limiting validator counts or by changing state requirements. We've looked at horizontally or vertically scaling execution through rollups. But coprocessing is a new paradigm. It's one that uses verifiable off-chain compute to scale the computation that existing L1 contracts have access to. So, what does that mean? And how do you use it? Put simply, there's a network. And this network generates proofs. And these proofs can be verified on any rollup or L1 that wants to verify the result of some computation. Right now, we're in production on 5 chains, Ethereum, and a number of L2s. And our provers are run by some of the top actors in the space, including Coinbase, OKX, Kraken, AltLayer, etc. So Lagrange uses these proofs in an interesting way. When an application on a chain wants to compute something that's not possible in its existing contract, what it simply does is emit an event. And it requests one of our gateways to generate a proof of a certain type. Once that proof is generated from our network of provers, it is returned back on chain and verified by the contract that requested it. So if your contract wants to run a big loop, it wants to compute over historical storage, receive of transaction data, it doesn't have to do that in Solidity or the language of your execution client. It can simply request it. Wherever it is today, it can now access more. So how it works, when you want a proof, you emit an event, you pay a fee, and our network computes it. And then we return that back on-chain. What makes Lagrange's approach to coprocessing unique? As many of you have hopefully heard by now, there are these things called ZKVMs, and there are these things called storage inclusion proofs and receipt and transaction inclusion proofs. How does this fit together? What does a coprocessor do, and what does Lagrange do, and how is it different? So Lagrange focuses on a unique approach to coprocessing based around verifiable query-based computation in the form of SQL. So, put simply, when thinking about computation over very large data sets, we want users to be able to think about that in languages that they are familiar with. It would be unnatural to ask you to structure a computation over 1 million rows and double-digit columns in Solidity. It just isn't what it's designed for. But if I asked most developers to define a query over a large table, a select query, for example, join, union across tables, you can do so in SQL. And so Lagrange lets you treat this on-chain data and scale your computation directly from your contracts over this on-chain data with a language that's suited for it. Now, what is the secret that lets us do this? Well, think of a ZKVM, proving an arbitrary computation, and think of an extension of that, in our case, proving SQL. A very similar conceptual architecture, but instead of proving generic Rust computation, we prove generic SQL computation. We call this verifiable SQL through decomposition. There's a new paper coming out very soon that presents this called Perseus from our research team. And what we do is we take SQL statements and we take how they execute as an abstract syntax tree, and we prove each of these operations as a MapReduce computation over the data. So we can take an arbitrary statement, see, for example, the one right here, select from, where, order by, and we can break this down into these primitives, create, range, project, sort, and arithmetic. Each of these we can then prove in parallel and recursively combine together, so the final proof asserts the validity of the query over blockchain data. And this is run with high guarantees of liveness from our prover network. So put simply, you can structure your computation as SQL. You can ask from your contract some computation, some query over receipts, storage, or transactions, and you can get the result back. And thanks to some of the interesting properties of the research that our team puts forward, such as the concept of updatable proofs, we're able to structure this in a way that is efficient. If you ask a query and then the underlying data changes, we can rerun the query without having to rerun the whole computation. Meaning, streaming data, large-scale compute over infrequently changing data are things that our systems are very well optimized for. Now, how would a developer go about using this paradigm? How would they interact with it? Well, 2 steps. First, being proving the origin of the data. Think of this as analogous to building your table, building your database schema. The second being querying and proving a query over that data. From a technical standpoint, we like to call this pre-processing and then proving of queries. Pre-processing is a very interesting construction that our team has pioneered. It's the concept of a vector commitment or a batch proof over blockchain data that's updatable. Say you want to structure a computation over 10,000 blocks. You want to create a table containing all the transactions that your contract received. Well, when the blockchain invariably changes, so will the composition of that table, and as will the proof of the correctness of the indexing and the creation of that table. That's not great because your computational complexity is linear with respect to the data. The more data you put in, the more expensive it is to prove the table. Our breakthrough is this concept of updatability in logarithmic time. So as the amount of data you're computing over changes, all we have to do is update the proof of the indexing's correctness and reform the proof of the table without having to recompute. Meaning that the amount of computation you have to do is proportionate to entropy, to the change frequency, not to the data size. A paradigm that is very efficient for large data sets. Wonderful. So when you think of this verifiable structure, it's important to think of it as provably equivalent, horizontally scalable, and, as I mentioned, updatable. Horizontally scalable means the more data you want to compute, we can generate these proofs in parallel across our network. And provably equivalent means you aren't trusting Lagrange and you aren't trusting the network. You have proof that this table was correctly formed from the blockchain data that can be verified back on chain. And when you want to compute over that, you want to ask the question, for example, who are the power users in my application? What have they done over the last 90 days? Should I give a discount to this user based on their volume? What is the volatility of this asset over some range of blocks? Well, you can do that, and you can request this query over the preformed table directly from your contract by emitting an event, which means you finally get a proof of something larger than what you can compute naturally in Solidity. And what makes this very powerful is you don't have to redeploy. You don't have to take your contract and deploy them with faster execution space on a new L1, on a new L2. You don't have to get into the whole question of the go-to-market timelines of the next exciting settlement layer, the next exciting modular stack chain. You can simply just take your application where it exists today and do a little bit more. So, as I mentioned, the developer flow, two questions. Firstly, indexing. Secondly, querying. From your contract, you can define this naturally without having to interface off-chain. You can request that a contract that your contract is indexed simply by making a call to hours. You can say, these are the storage slots I care about. Here is the size of the storage slots I care about, the mapping I care about, and here's my contract errors. And then obviously funding, you fund it. From there, all you have to do is wait till you want to query. And when you want to query, you emit an event indicating that you want something to be computed, and you wait for the callback process. Obviously, depending on the size of the computation you need, the proving time can be variable. We talked a little about asymptotics before and the proving time. But at its core, it's an asynchronous computation that exists and scales any existing blockchain. So here is a whole end-to-end flow of how it would work, both in a single chain or a cross-chain context. The final proof that you get is verifiable against the block header of any chain that's computed over, which means if you have the block header of Ethereum or of Optimism or of Base, you can verify a proof of computation over it. So in any chain, you can access your block header from block.header and Solidity. And cross-chain, you can access the Ethereum block header from many of the rollups that actually use Ethereum for their canonical bridge. Which means you can really just take the access to data that you have and start doing a bit more with it. And so in this example, we have a chain, say blockchain 1, that requests the creation of a table and requests the creation of a series of queries. Then you have our network that is responsible for generating these proofs of this computation and returning them back on chain. It can return to chain 2 that can access the block header of chain 1 already, or it can return back to chain 1 naturally. Now, Lagrange has been deployed in production, our proven network, for the last 60 days. We have generated close to 2 million proofs across a series of ecosystem integrations and with some of the best operators in the space running our infra across 5 chains, and we'll be scaling more soon. So to close things out, I want to make it concrete and hopefully discuss some use cases that would inspire some people here to build something new with this paradigm. One of the commonly asked questions in common development practices in Solidity is the use of reward-bearing contracts. Think Sushi Master Chef or points programs for major LRTs. The question they want to ask is very simple. Has user X held asset for a series of blocks where the reward that they're eligible for is proportionate to the amount of blocks that they've held the asset for? Very simple question to ask off-chain. Very simple question to ask to a database. Not a very simple question to compute within Solidity, where access to historical data is limited. And so with this type of computation, this type of proof, you can very naturally ask this question, and you can very naturally verify the result without having to deal with a series of complex and risk-prone Solidity engineering practices. And so this is generalizable to really any type of group. Let's say you want to incentivize someone to hold an LP position within range on UDV3 for your asset pair. Simple. You can verify the proof of that computation over the data back in your contract. Which means the DeFi instruments that you can build are in fact a lot more expressive now than what you could before. Another exciting use case that is personally close to my heart is NFTs. I think we've seen a lack of focus on NFTs in this most recent cycle, but I think they are integral to the fabric of what crypto is, the creation of culture on-chain. One of the limitations of NFTs is utility. I own this token, I've never sold this token, let's say. I own a Pudgy since Mint, let's say. I don't, though. Let's pretend I do. Well, how do I get a reward for that? How is a contract developed by Pudgy going to be able to reward me for my loyalty, or Azuki, or Sappy, or Miladies, or any of the major projects? They can't access really ownership history from their contract. They can't access the length of ownership history from their contract. The complexity of the on-chain solution and the utility of my NFT is constrained. With a coprocessor, you can just simply think of the NFT contract data database. And from your contract, you can ask questions. Does Ismael own an NFT with this series of metadata? If so, give him a discount here. Is Ismael loyal to this NFT project? Has he held this asset for a period of time? Is he a flipper? Maybe he gets access to the next mix because of this proof. These are the types of things you can build, the types of things you can start taking aspects of crypto culture, integrating them in new ways into on-chain experiences, all powered by ZK coprocessing. Now, what's next for Lagrange? How can people here who find this interesting get involved? Well, I would first suggest that anyone interested go on our GitHub or our docs and start exploring. Explore our partners, explore the integrations that we have, explore the functionality of this technology, and follow us to stay up to date on some big changes that are coming soon. We have a very big launch coming off 4 weeks that we think is going to really move this scalability paradigm into the mainstream. Projects that exist today can access this type of computation directly from the chains they're on without having to read a code. And some of the teams that are embracing this new paradigm, I think, will really put it on the map. So, on a personal level, if anyone here also would like to build with this, please reach out to me on Twitter or on Telegram at Ismael_H_R, or follow us on Twitter at Lagrange Dev. Thank you guys so much.